Yes, welcome to this presentation. My name is Koenders. This is a presentation on reporting the progress of TC 270 CIM, so benchmarking chloride ingress models on real-life case studies, theory and practice. That was the original title. I was the chairman of this committee, and the deputy chair was Keiichi Imamoto. So what you see here are the two, because we're talking about modeling and benchmarking, we had two structures selected. One marine submerged, that is the picture here, and we had one road sprayed structure used for the activities, the benchmarking activities. And that was done because of the different boundary conditions. So the marine submerged structure has a constant chloride load, let's say constant surface concentration because of the water, the constant chloride concentration in the water. Whereas the road spray structure has the only in the winter times when de-icing salts are used, so that has a non-continuous surface concentration of chlorides. Yeah, that's why these two were selected, and they were used here in this this TC. Yeah, so we had many meetings in this technical committee, and one of the meetings you see here, we had many active. Especially in the beginning, and we had many active members. But it was not easy. Yeah? It was not easy to structure this work. And you see here, this meeting is in Darmstadt in 2017. And that is what finally we could manage to get a nice work done. But in the beginning, you see, we really needed a lot of time to structure and to focus the TC work. Here you see the screen dump of the Rilem TC website. So in total, we had 12 TC meetings, I checked. And 5 of them were online meetings because of Corona on the one hand, also because of, it was easier in the beginning also to do some online meetings. But in total, so 12 meetings was what we did with the committee together. And also an important point is what you see here is that we started in 2016. So now it's 2021. We needed, at least 5 years to complete this work. This is where it all started. It started in 2015 in Japan. I was there for a conference and with Keiichi Imamoto here, this picture, and also with Ichida, Professor Ichida Tetsuya Ichida, we discussed this topic and came to the idea to set up a TC for this. Why? It was in Japan, many problems on traffic, so durability driven, on corrosion, durability driven, corrosion driven durability issues, many problems, highway, bridges, and many questions came up about how to use models for this and how accurate are the models to predict this, finally the service life, right? Also, it's not only in Japan that problem, it's also in Germany, or it's actually all Europe where this problem is going on. Actually, as we speak, at this moment also many construction sites on highways in the Netherlands, in Germany, everywhere you go. You see the same problems, that bridges are reaching their end of life and have to be replaced or repaired. Yeah, most of this was a study from Schiessel, Professor Schiessel, 2007. It's already long ago, but it's clear that chloride-induced corrosion, so chloride ingress, is mostly the cause of the corrosion problem. That's a dominant mechanism that leads to corrosion. Other problems are as well causing quality reduction or durability problems of structures. You see here fatigue, of course, carbonation, frost, And but here also what is interesting is the poor workmanship. Yeah, we can also reach a better quality there. So from a modeler point of view, this corrosion is a problem of just a few parameters, right? We have this surface concentration, which is a parameter that is given by the environment surface concentration. We have the diffusion part, which is the medium that transports, that moves, yeah, that allows the chlorides to move through the cover, concrete cover. And then we have a critical chloride concentration, which is a kind of criteria, but that is even further away for a modeler. A modeler just looks to how can I simulate the chlorides moving through the cover. It's a very complicated problem, actually, especially also during one of the meetings that was in Copenhagen at the COBI Consult. We had a very good discussion on all kind of different philosophies of models developed over the years, and some work with free chlorides and also with chloride binding isotherm is such a thing that you have to consider, or some models consider it, and other models work with a constant diffusion coefficient in space, and so all these difficulties were there, and we had to structure it in a way, and that's what we did, at least try to do. So with the questions that came up is, so what are we now finally doing in this committee? So how to model chloride ingress, that's what we wanted to know, and how to classify these models, yeah? These chloride ingress models, how can we classify them? And so that means also that we did not consider surface life. So we did not go that far for doing a probabilistic analysis, surface life analysis, cracks or corrosion. We all did not consider that. So we really boiled down to the very basic question of how do the chlorides move through the cover, right? To simplify the problem. Yeah, so if you then look to a model, I draw here this black box. Yeah, they normally say it's black box. So the model is very simple, actually. So we have a model, we have input and we have output. And so how is it then possible that we have such a big variety? Because most of the models, if we have an analytical model, they all use the same mathematical formulation. And so why is it so difficult? So, and what can calibration do to improve that? So we have at least a couple of problems here, a couple of parameters which we can discuss and which we also analyzed in the TC. So when you go back to the mathematical basics, then the fixed second law, or fixed first law, fixed second law is the one differential equation that is very frequently used, because you can find a very nice analytical solution for it, and that's written here. And then later we also added this time-dependent diffusion coefficient, right? So, and then the famous aging factor is there, which only, which makes it even more complicated. Yeah, right. So this is an analytical formulation, which finally, if you look to the formulation itself, we have here the surface chloride concentration, and we have here the diffusion coefficient, and we have here the depth. So the parameters where you can play with are not so much. Yeah, and then of course not forget the aging factor. The other models which are also used for chloride ingress modeling are the numerical models. They also have this first fixed second law part, right? So this transport in X direction. But they also, some models have a convection term, and also some models use even a binding term, chloride binding, and then they differentiate between free chlorides and bound chlorides. Now here you see that. So there is then a relationship which you need between free and bound chlorides, which you also have to measure in a way to find that relationship. Yeah, so that makes it complicated. There are also some models, they use this Nernst-Planck equation, so the ionic interactions between the chlorides, and that's even more complicated. So there is a whole scale, a whole variety of models, a numerical, but the basic classification is it the numerical model, right? Then you have more flexibility, or is it an analytical model, which is which is limited, has limited flexibility. Yeah, so what we did is these two benchmark cases. I told it in the beginning that we selected this marine submerged, how we call it, that are here, these concrete panels. They are in the seawater in Sweden. There's a field experiment where they were already exposed to chloride seawater for a long time. And we had this road spray case from Switzerland, Bonadou's experiment, where here these three concrete panels are there and they are exposed to sprayed chlorides by de-icing salts, and they are measured already also for a long time. So we use these two, one for a constant boundary conditions chloride surface, and one for non-constant, let's say. Yeah, and then we have this analytical and numerical models and see how they perform. We had 14 models in total that participated. So we had active modelers. Here are the names of the modelers. They were all very much involved in this TC from different countries all over the world, actually. And yeah, it was very nice that we had such a big group of models participating in this TC. Starting with this marine submerged, we had input 0.6, 1, and 2 years. Data was provided to the modelers, to all the modelers. And then the question was, give us a prediction for 5, for 20, and for 100 years of chloride profiles. So this was the input. This was the measured data from these panels. And yeah, the question is then, and we also give them other data for the cement type and everything. But so everybody had the same input data, and we asked them to come up with these predictions. Then it's good to know that these panels have also an infinite space, and this analytical model, which many modelers used, is A is for analytical, and N is for numerical. It's a semi-infinite space because the thickness of this these plates in the water were 10 centimeters, and it's good to know that this analytical formulation is developed for an infinite space. So you also have to take care of that. For numerical models, that's simpler because you can just take this infinite space and model it. So this was also an issue we had to deal with. But it's nice to see that that we had all these models involved in the predictions, and then for the first prediction after 5 years of exposure, you see all the models participated, the modelers and the different models, and you see that after 5 years we had this profile. You see these black dots are the experimental data measured, and the other ones are the predictions. And you see also that these numerical models, they have a different course. Yeah, they take also these, some of them, they take this carbonation effect into account in the surface zone, and others do not. And the analytical models, they do not have that. Yeah, they cannot take that into account, but you see that there is a very nice result. Yeah, the total, after 20 years, total chloride concentration, you see the spread is even bigger. And after 100 years, we had even a bigger, wider scatter of the results. And also here you see the difference now very clear between numerical and analytical models. So the question you can ask yourself now is, why is this happening actually, right? It's not about which model is good or which model is bad. It's not, the question is why, Why? Because we all had the same input. The model structure, the model, the mathematical backgrounds, especially of the analytical models, is not so much different. So why is this big scatter existing? So what we did is a reverse analysis on the data, which we got from the which all the modelers generated, and then for the diffusion coefficient and the surface concentration. Also for the aging factor, but that was a bit more complicated. I don't show you that. Here I show you the results for the surface chloride concentration. So this was the reverse analysis, and you can see that although everybody got the same data, that the surface concentration taken by the modelers differed between 3% and almost 6% in the end over time. So this is the time X goes to 100 years. So it's a matter of interpretation of the input data. So, and then the analytical models, they have a constant surface concentration, but the numerical ones have even, they have with time, they can change that, of course. The numerical models have this possibility. Yeah. So the diffusion coefficient is even you can see it is almost 1 order of magnitude difference for all the models participated in the benchmark. That although the what I said, yeah, that everybody could fit it, the data, the input data, there is a kind of interpretation difference, right? It's modeler dependent. So that was what we did with the marine submerged case. So the road spray, that are these 3 panels, and these 3 panels, they consist of a base slab here, and then you have here the 3 concrete panels. They are 3 specimens actually, E1, E2, and E3. They're 20 centimeters thick, and they are in Bonadous. It's from we got this data from SGK from Switzerland, and yeah, that was great. Yeah, that we could use this data. The compressive strength of these concrete specimens, they were cast in 1995, and we see here E1 and E3 data only. After 7 days, 33 megapascal, and that finally after 90 days was 47. 47 and 50 for E3 was the and 54 year after 1 year, the compressive strength. Yeah, so we have many information from these tests. Was given to us by Jan Bishop. He had all this data, and also the temperature fluctuation over time. So this is for a couple of years. We had all this information, which could be used by the modelers. Here also the precipitation, so the rainfall, let's say, over the years, per month, and then the scatter per year, which could also be taken into account, maybe for surface water on the surface of the concrete panels, affecting the chloride ingress. And here we have the de-icing salt for the road, yeah, total use of NaCl on this area, which was the roads there in this area. And from that you can recalculate how much salt would be spread on these structures. Right, so this information was all available, and then they also provided us with these chloride profiles. So this is E1 specimen, and this is the depth. And here we have the E3 specimen, and it was very nice. During the TC work, they also did an extra test measurement. And so that means that we had also data from these specimens up to almost 22 years. Yeah. So you see here 1.6, 4.4 up to 22 years. And this data could be used by the modelers to simulate. So the tricky thing here is that the chloride spraying of the chloride due to traffic is only in the months, let's say December, January, there in that period of time, period of the year, and then the rest is nothing. Yeah, so it's a clear non-constant chloride load which you have. For models, this is very complicated to simulate, and even for analytical models, it's even not possible to do that. So we had only the numerical models participating in this exercise, in this benchmark. The first one was from COE. There was the Melgro-Polston model, was then used by COE. You see, it had a very nice result. Up to 70 years was the prediction, and even this black line here is the 100-year prediction. This model was used by Tang, looping Tang from Sweden. Also very nice prediction, and even here the carbonation effect in the beginning could be used by his model. And then we have here from Anthony Soive from Zarema, also very good prediction. I must say that all the details which are and assumptions used by the TC members, by the modelers, are very nicely described in the report. So for that, you can find more detail in the final report. Some models had even was more difficult to have this non-constant. To make this non-constant over time, this chloride boundary condition, and then you see also that you have that there are more difficulties to predict this chloride load. Although I must say that also this was done by Lars Olaf. This was the first. He was the first, doing this, and it was very nice. He gave a very nice presentation, and the results are actually very good. Although they are not really matching with the data, but the whole interpretation of how you have to deal with this, how you can anyhow get a kind of result from and can do a prediction with these complicated chloride loads, which are non-constant with time, is all described in the STAR report, and also this explains what you see here and why this result is what you see here. So finally, to come to an end, is what we did with this TC is we had these two cases, marine submerged and road spray, for benchmarking the models. Two cases are calculated, so we had two cases, two classifications, analytical and numerical models were separated. In the report, we also added some basic guidelines for calibration, and we have proposed, because I think the calibration is something where a lot of improvement can be reached by a good calibration method. The writing of the STAR is done. It was an enormous work, I must say, to write a STAR report. But many of you know that already, but it's a huge job to do. But finally, we managed to get a very nice report. And the publication of this report will be in the fall, I hope, in somewhere in a couple of months, maybe. Yeah, so thank you for the attention.